The ARM v8 architecture, which you're familiar with, advances pretty much annually with a regular tick, which introduces a number of small-scale increments to the architecture. And the latest version is ARM v8.5, which you're probably aware of. It was announced last year. This presentation is not about the next annual architecture tick. You'll hear about that later in the year. Some architectural features that we add are too large to fit into a typical, the smaller annual cadence. They require much more effort to develop and are the result of several years of effort. And I'm here today to talk about two of those new architecture technologies that we're introducing to this audience, and which are intended to provide a major increment in the amount of performance scaling that can be achieved from the architecture, from the ARM architecture. And as I said, they are the outcome of many years of architecture research and development. But, and this is an important point to make here, these new technologies are not yet part of any announced product roadmap. They're not yet part of a formally announced CPU product roadmap or a formally announced ARM architecture version. I'm here to instead reveal these to you and the open source community in order to allow us to begin the process of upstreaming software and tools for these technologies to work with you, collaborate with you in developing support for the architecture. This is a task which, similar to AArch64, which took many years to ferment and grow. These kind of new architecture technologies need many years of development before we actually announce the architectures publicly and announce CPU products that support them. So, I talk about performance scaling. Why am I talking about performance scaling? It's because, as you probably know, people talk about this all the time, we are now running up towards the limits of Moore's law scaling. So, somewhere back in the 1970s, Gordon Moore, then of Intel, predicted that silicon technology would improve so that you could double the number of transistors on an integrated circuit approximately every 2 years. And that pretty much held up for 30 years or so. But we are now beginning to see the tailing off of that curve. It's not stopping. We are still shrinking geometries, and this chart here is looking at the annual, well not annual, but the regular tick as silicon geometries shrink, and we can put more transistors on a processor, and that's still happening, but each step is taking longer. I'm sure if you're following Intel, you're aware of that, and the increments you're seeing are smaller. And more importantly than that, not only is it getting slower and in terms of the rate and in terms of the decrease in geometries, but also the cost of achieving that is increasing hugely. So it's becoming much more problematic, much more expensive to get this extra scaling. But that's just area. Probably the more interesting thing is that as a result of this shrinking transistor geometry, we've also achieved on that same biannual tick, generally speaking, for the last 30 or so years, an increase in frequency as well of about 40% every 2 years. So the combination of decreasing transistor size, meaning you can fit more gates onto a CPU, and the increase in frequency allows far more adventurous microarchitectural tricks to deliver more performance. But we are beginning to run out of that, because now if we look at Moore's law applied to a single thread performance on a CPU, we can see an even more dramatic scaling off. As we get up into this decade, we can see we're going down from sort of 52% a year on average to around 3.5% increase in single thread performance per year. So some real hard limits coming here. So how can we try and address this tailing off in Moore's law? Well, we can still build these extra transistors, but we can't get much more frequency out of them. So how can we use those additional transistors that we can build to unlock more performance from our CPUs? One way to do that is by processing more instructions or more data in parallel per cycle. Now, my friends who work on CPU microarchitecture and CPU design in ARM do some amazing tricks to extract more instruction-level parallelism from your code, existing serial code. And there's some real ingenious tricks to be done there with things like out-of-order processors with multiple execution pipelines and such like. Out-of-order execution allows us to get a big increase in performance by executing more instructions in parallel. But there is a limit to how far that can go. We are beginning to also, although we're not there yet, we can see that there is a limit to the amount of microarchitectural trickery that we can do. So can we instead think about, rather than microarchitecture, think about architecture? And in particular, I'm talking here about instruction set architecture, because that's my field. Can we, with our instruction set architecture, find ways to express greater parallelism in our code, in the code that we're generating to run on the CPU? And by doing so, try and tackle this, the other law, we've had Moore's law, the other law that we need to care about is Amdahl's law, the unbending nature of Amdahl's law, which we really can't avoid, which tells us that the more that we parallelize our code, the more that the performance of the remaining sequential, unparallelizable code becomes the determinant to performance. So unless you can actually parallelize an awful lot more code, you're not actually going to deliver any additional performance at the bottom line to your applications. And then how can we do that without us having to go and rewrite all of our code in order to achieve it? I mean, you can build software that uses heterogeneous accelerators and such like, but to do so requires a major restructuring and major rewriting of the way we do our code at the moment. What I'm proposing here and introducing to you are two new architectural features which are designed to increase parallelism beyond what we can do with just instruction-level parallelism. So first of all, the Scalable Vector Extension version 2, or SVE2. And this is designed to achieve greater scalable data-level parallelism for a wide range of applications. SVE2 is built on the foundations of SVE, which if you attended the Fujitsu talk this morning, you will have heard about how successful that is in HPC. It introduced the concept of a scalable vector length, a variable vector length, if you will, where the hardware, the implementation, gets a choice of building vectors between 128 and 2048 bits. Fujitsu's implementation is 512. You could imagine that other devices with more constrained power consumption, for example, might well be building smaller vectors than that. But it also introduces as well a concept which is the vector length agnostic programming paradigm. And that's a feature of the architecture which makes it possible to write code once for this architecture, for this instruction set, and for that code to scale automatically, dynamically at runtime to the available vector length provided by the hardware. That's pretty attractive if you compare it to a number of other architectures where if you have a different vector length, you also have a new instruction set and you have to rewrite your code every time for each new instruction set. It introduces concepts like predication and gather, scatter, load, store, which allows much more code, more complex code with complex control flows and nested loops and such like to be vectorized. And it also contains other features which are designed to tackle some of those barriers to auto-vectorization, some of those aspects which impact on Amdahl's law. We want to be able to, if we've got this technical term, honking great vector unit, we want to make sure that we can generate as much of that vector code as possible to exploit that. So it begins to address some of those issues that prevent that. So SVE2 builds on that foundation, which is a great starting point, and we always intended with SVE, when we introduced it for HPC, that it would be the starting point for our vectorization technology going forward. HPC was a really good place to land it initially, because that's a community that has the software tools and has the experience to know how to exploit that and to start to build a software ecosystem. But it was always our intention that we would take it further. And with SVE2, what we add is the, first of all, the NEON style functionality that was missing from SVE. SVE was just for HPC applications, just simple integer and fixed point data types. We now introduce all of the NEON style, DSP, fixed point type multimedia operations. Plus, we introduce a number of other features designed to accelerate other interesting applications that we are aware of at the moment and that are becoming important in the ARM ecosystem. So the goal was, with SVE2, that it should have performance parity at 128-bit vector length with NEON code. There should be no good reason, if you're targeting a device which has SVE2, not to write that SVE2 code. You should be able to get the same level of performance from that. But, obviously, you then gain that scalability. As you move on to a processor with wider vector lengths, your performance increases as your code scales to that vector length. And also, we again go further with tackling some of these obstacles to auto-vectorization to make it possible to extract more parallelism from ordinary scalar code. Now, we also wanted to look at a number of other applications and see whether we could accelerate those. So there are multiple use cases we've tried to address with SVE2, and that includes applications in a range of different areas like client, edge, server, and again, HPC. So things like DSPs, codecs, filters, and so on and so forth. And the goal here is to improve the competitiveness of the ARM-based CPUs relative to proprietary or specific accelerators, to make the ARM instruction set and ARM processors more sticky, if you will, to give you a single architecture to code for rather than multiple different architectures to code for. And to reduce the amount of effort required to port software and then deploy it in the future onto new processors with wider vectors. The other key feature we're introducing, as well as SVE2, and which is tackles the other dimension of parallelization, is the transactional memory extension. So transactional memory extension is designed to deliver scalable thread-level rather than data-level parallelism for multi-threaded applications. So why have we done this? Well, it has to, why have we added hardware transactional memory? Obviously, a very important part of that is competitive pressure. Other architectures have had hardware transactional memory available for a while. They've taken a number of attempts to get it right, and I think that now it is available in a usable form on some real hardware. We expect that software will now begin to take advantage of that, and therefore ARM needs to have a solution for this technology as well. Otherwise, we lock ourselves out of applications which are targeting this particular feature. So we have to have it in that respect, but it brings this additional benefit, which is as well as just being compatible with other architectures, it introduces this other aspect of parallelization. And it's the combination of these two things, as we'll talk about later, that is really interesting. So TME introduces the concept of strong isolation between multiple threads. Code that is running inside a transaction in transactional state is completely isolated, is strongly isolated from other threads in the system, whether they are transactional or non-transactional. And failure is atomic, as in a transaction either fully completes and all of the operations that it's performed inside that transaction are visible to the rest of the system, or it fails, and all of the architectural state changes that it's made are wound back and are not visible to the rest of the system. So it either succeeds completely or fails completely. And HTM, hardware transactional memory, is a great solution for certain classes of multi-threaded application, not necessarily for all of them. It's most appropriate for multi-client applications, so server-type applications generally with multiple clients, where there's a big sparse data set that is lightly contended. And examples of those obviously are databases. People are pretty familiar with database, transactional memory for databases, but also for things like network data plane, routing tables, and such like, and also for things like web serving, dynamic web serving as well, where you have a large internal in-memory database of pages to serve. But probably most importantly, like SVE, what it does is it allows us to simplify the software design of massively multi-threaded code. And we'll look at that in a few slides later on. The key feature here, the key technology here is a concept called transactional lock elision, which allows us to use hardware transactional memory for existing threaded code with no need to actually rewrite it at all. If you're using Pthreads, you just get it for free. Okay, so a quick recap on SVE for those people who aren't familiar with it. SVE has a number of key features: gather, load, and scatter store, which allows us to transfer data from non-linear addresses in memory into a single vector register and vice versa. And this allows us to vectorize code which deals with real-world data structures, complex data structures with indirection and such like, rather than just simple buffers in memory, which is what you can process conveniently with NEON. We have the concept of predication, per lane predication, which allows you to control which lanes of a vector are being operated on and are generating results for each operation, and protect against faults occurring in lanes that you don't care about, and vectorize more complex, as a result, vectorize more complex conditional code and nested loops and such like. Also, and this is an important feature of SVE compared to other vector architectures, that the predication in SVE is absolutely fundamental. It's designed from the ground up as a predicated architecture rather than having predication bolted on afterwards. So the whole way that you write your code in SVE is based around the predicate. And the predicate is used to do all the loop flow control management. And this significantly reduces the amount of overhead required to vectorize your code. It removes a lot of the loop heads and tails that are often required for vectorization, but also a lot of the other sort of loop management overhead that is associated with vectorizing. And what that does is it allows compilers to be much more aggressive, potentially, about vectorizing your code, even at O2, because, as we'll see, you can vectorize code without any significant overhead in terms of code size. Other key features are software-managed speculative vectorization, and this is essentially to support do-while type loops, or loops which contain break statements, where you don't know in advance where the number of iterations of the loop are unknown at a compile time, or even when the loop actually begins execution, where the loop termination point is dynamic. Typically, a compiler will refuse to vectorize such loops. SVE allows those to be vectorized. So again, this is all about tackling some of those difficult to vectorize programs. And then a whole load of extra additional vector data processing instructions, which are probably not worth going through in great detail, but a number of other things that make it easier for a compiler to vectorize more code. SVE is an adjunct to NEON. It doesn't replace NEON. It extends the NEON 128-bit vector registers, V0 to V31, with up to 2048 bits per register, depending on the implementation. That's an implementation choice. And includes support for full range of floating point, double precision down to half precision, and all the integer formats fully packed into the vector 8 up to 64 bits per element. But as well as extending the vector registers in such a fashion, widening all of our vector registers, it also introduces a new set of registers, the predicate registers, and these are also scalable. So predicate registers P0 to P15, 16 predicate registers. The first 8 can be used for what we call governing predicate registers, which are used to control individual vector instructions, which lane, it says for any given instruction which lanes are active or inactive, for loads and stores and general arithmetic operations. And then there are another 8 predicate registers, P8 to P15, which are used as effectively additional predicates for predicate spill-fill, potentially, but also for things like loop management. I mentioned that you use predicates a lot in SVE for doing your loop control. So you have additional registers, predicate registers for managing the additional loop control. And then finally, there's a dedicated predicate register called FFR, which stands for the first fault register, which is used for managing the software speculative vectorization. So here's an example of how SVE can be used in a very lightweight way by a compiler to vectorize some code. So this, I think you may have seen this, actually a version of this if you went to the Fujitsu presentation this morning. This is a SAXPY function. It's a very simple loop going through 2 arrays, and it's calculating scalar A times array X plus array Y. Really very simple, but it's enough to show us what's going on. So this is what you might get if you compiled it without too much vector optimization for the standard A64 scalar instruction set. And I won't go through the details. I'm sure you're all very familiar with that. But essentially, a simple loop, reading 2 elements from the 2 arrays, doing a multiply add, and then storing the results back to memory again, and going up 1 element at a time. And the important thing just to highlight here are the key control parts of the loop. So we've got an initial branch at the beginning to the condition of the loop condition, the latch condition at the end of the loop. We've got our increment of the pointer or index by 1, and then we've got a comparison and a conditional branch back to the beginning of the loop. So here's what the same code looks like for SVE. And what you'll notice is, really, it doesn't actually change very much in terms of the amount of code. We don't have any loop heads or tails. We haven't introduced a lot of extra code to manage the predication. Here is a loop which does much the same thing, loading from 2 arrays, doing a multiply, accumulate, and storing the results back, but now each instruction is operating on multiple elements at a time rather than 1. And if we compare here the control flow instructions, if you like, for the loop, what's happened is we've replaced the scalar compares and the scalar increments by these new SVE instructions. The while instruction in particular is the key instruction for SVE, which allows you to iterate through a loop, generating a predicate for the next iteration of that loop, and at the same time setting the ARM condition code flags to handle the final branch at the end of the loop. So it effectively combines the predicate generation and the increments and the condition code test, condition code generation into a single instruction. So what you can see from that is a compiler can actually say, I can now vectorize that loop for SVE, which I might not have done for NEON or other vector architectures, because unless I knew that this loop iterated enough times, I might not have wanted to vectorize it because it would have bloated my code too much. Code size is now essentially identical. So a compiler can be much more aggressive about vectorizing code for SVE. You can write the same code as well using vector intrinsics. I'm not going to go through this in detail, but again, you can see the difference here. On the left, we have this code written using NEON ACLE, the ARM C language extensions, vector intrinsics, using fixed length vectors. Float 32 by 4 is 128-bit. That's the NEON fixed length 128-bit vectors. reading 4 floating point elements at a time, doing the multiply, accumulate, and storing them back. On the right, we have the equivalent using SVE, ACLE intrinsics. And now what happens is we have new data types. We have these variable length vector types, SV float 32. That's a scalable vector float 32, which effectively is a variable length type. In fact, we actually call it a sizeless type. And then a set of intrinsics which operate on that, essentially one full vector at a time per iteration. So this is equivalent to the loop, the assembler code that you saw on the previous slide. So you have 2 ways of writing it. And how does that actually result in, after all of this, what do you get in terms of performance? So as I said, this was an HPC extension. And so these are some well-known HPC benchmarks, and this picks a handful of them. I mean, this is reasonably representative from a set of HPC benchmarking workloads. And initially what it's looking at here is the amount of additional vectorization that can be achieved by SVE over NEON. So on the left-hand side, the gray bars are showing us the increase in the amount of, in the dynamic count of vector instructions that we can achieve from using SVE. So anywhere between about 40% and 70% increase in vector instructions, which is pretty significant. And then in terms of performance, what that means is we actually get an uplift in performance. Now this is speed up on the right-hand side of the scale, the blue line. This is the same vector length as NEON. We can scale anywhere up to 3 times the performance by virtue of the fact that we're vectorizing more code, and then take exactly the same binary and run it again, and but now at a 256-bit vector length, and now we're scaling performance up to 5 times NEON. Or if we go up to 512 bits, for example, as in the Fujitsu machine, up to about 7 times the performance. And that's without recompiling the code. That's just changing the vector length on the, in the emulation, or in the model, or in the hardware. So, SVE2, that's the where we started from. That was SVE, as in 2 years ago, 2017, we announced that. SVE2 adds a range of enhancements, and I'm not going to go through this list in detail, bedtime reading. But the key feature that it's adding is support for all of the NEON-style DSP media type instructions, the NEON fixed point, widening and narrowing type instructions. It also adds a number of new instructions designed to accelerate particular workloads that we care about in the new ecosystems that we're looking at. So we have fixed point complex .product instructions, we have interleaved add with carry, and so on and so forth. So there's a bunch of extra arithmetic instructions to accelerate use cases that we have identified as important to ARM and its partners. Things like histogram instructions to accelerate computer vision and vector sorting algorithms. Non-temporal gather scatter to support cache segregation, which is important for certain types of sorting algorithms and others. A set of extended bitwise operations to support things like CRC and ECC. Bit shuffles for things like radio baseband processing, compression technologies, genomics, video codecs and such like. The NEON-style cryptographic instructions, and then a set of other miscellaneous enhancements to improve the, again, the ability of SVE to vectorize more code. So it's a set of new data processing extensions which extend on the base. It's a complete superset of SVE. It's everything that SVE had, with a new set of data processing operations added. The only change, though, as far as the Linux kernel is concerned, there's no. If you've got an SVE-enabled Linux kernel, the only change you have to worry about is you've got some new ID registers which identify the presence of these new functions, these new features. Otherwise, the Linux kernel is unchanged by this. SVE2 also has some changes to the semantics of NEON narrowing and widening instructions for reasons of the way that you build the widening and narrowing in a wide vector machine. We don't want to have widening and narrowing that moves data across the full width of the vector. That's a very expensive operation. So the NEON style approach of low, high vector doesn't scale to very wide vectors on SVE. Instead, for SVE2, we instead use a de-interleaving type operation where we use even or odd elements rather than low elements and high elements. So there's a subtle difference to the way the code is written there, but in practice that actually makes very little difference to real applications, because in general you widen, you do some processing, you then narrow back again, and everything ends up back in the same order again. What does that mean in terms of performance? I said at the beginning one of the goals here was that we should be at parity with NEON at 128 bits, so there's no reason not to use SVE2. And so this is a set of a basket of DSP type and media type workloads that we used as part of our initial investigation. And it shows the performance at 1.0 here of a NEON optimized code. And then below that we have SVE2, initially configured at 128-bit vector length. And the result is broadly the same. It's slightly higher. Some of that may be to do with using some of the new instructions that SVE has. But broadly, the same performance from SVE2 as NEON. So the new vector length agnostic programming style of SVE does not add any significant overhead to existing NEON code. And then, but of course you then get the benefit, which is on the wider vectors, you can now scale that performance up from what you can achieve with NEON to use your wider and wider vectors. Hi.
Can we interrupt?
Yeah.
So just to clarify, this is the same code that's running on default implementations of the SVE?
Obviously, there's NEON code and SVE2 code, which is different, so the different instructions. Yeah. But for the SVE2 code, now, it certainly for the 256 and 512, that's true. I think for the 128-bit version, there were actually a few of them that were hand-coded specifically for 128-bit. They had a dynamic test in the code to say, which am I running on? But essentially, most of, I think probably 80% of the code there is exactly the same binary running on both. I mean, there are a few things like FFTs and FIRs where it actually sometimes helps to know what the layout in the vector is, and you can do you can do a better job if you make it vector length specific in that case. But and then extending that from DSP to general performance. So again, we've got the similar graph to what we showed for the HPC one, but now we've got a lot more benchmarks in here. We've got sort of Embassy and some HPC and other DSP tests and so on in here. And we see a kind of similar picture, which is a lot of extra vectorization, that's the gray bars, which can be achieved by SVE, and that gives, depending on the quality of the compiler, it may give some additional uplift, and scaling to the right you can see some very high uplifts. The speed up is on the left-hand side scale, so up to 8 times and a few of them there. And that's at 128 bits, so that's the same vector length as NEON. And then if we go for 256 bits, you can see we can get some additional uplift now beyond what NEON can achieve by using the wider vectors. So that's SVE2, Lightning Tor. TME is the other key feature, transactional memory. And pretty much this is TME. It's actually 4 instructions, but these are the 2 that you probably care about most of the time. T-start enters into transactional mode. Assuming there's no failure, it returns you back a value in the register argument of 0, saying everything worked, carry on, you're in transactional state. If it returns a non-zero value, you've had some failure case which you need to then handle in software. So this is not hardware lock elision. This is equivalent to the TSX restricted transaction mode, where it's up to software to implement the fallback cases. So it provides the strong isolation, which I mentioned at the beginning, non-interference and containment from both transactional and non-transactional code, failure atomicity, with best effort transactions. So the important point here is it doesn't guarantee forward progress. It is up to software to implement the fallback cases and to implement some sort of retry mechanism. So assuming that you don't get the error, you start the transaction, you execute a sequence of operations inside the transaction which may read and write memory, but none of that becomes visible to the rest of the system until you execute the T-commit at the end. When the T-commit is executed, all of the architectural state that has been changed in registers and memory is committed and is visible to other software and hardware in the system. If the transaction fails, all of that state change is unwound. You're returned back to the T-start instruction with a result code that tells you why the failure happened. Yeah.
What's the maximum amount of memory you can read and write in the transaction?
That is not fixed by the architecture. We make some recommendations based on a set of benchmarks, so the stamp benchmark set, for example, where we're going to be specifying in SBSA a set of recommendations for all implementations so that we can get some consistency of behavior across all implementations of the architecture. But certainly the initial goal is to be no worse than is achievable on the Intel architecture. These are just the set of error codes that you can get back. Probably the most important one is this is what you get back in your register after the T-start. The most important one is the retry bit. The retry bit says it's worth having a go and retrying this operation. It's possible that it was a transient failure and you may succeed when you retry it. If the retry bit isn't set, then basically give up. You need to run some fallback code to implement the operation in a traditional manner using locks. The killer use case, and I mentioned this at the beginning, for transactional memory is transactional lock elision. What this allows software to do is execute a traditional, use traditional locking mechanisms to protect critical regions, critical sections in the code, but to have those automatically replaced by have the lock and unlock automatically replaced by a T-start and T-commit. So it converts what was effectively a serialized operation controlled by a lock into an operation that can actually be performed in parallel inside a transaction. So exactly the same programming model as the locking model, but now all of your critical sections run concurrently unless there's a conflict, of course, in which case they will have to retry. So and if you do execute the fallback code, essentially it's actually straightforward. The fallback code just takes the lock as it would have done before and executes the code with the lock set. So the GNU-C library already supports this, thanks to some of the other architectures that support transactional memory. There's already support in Pthread mutex lock for this, and we will be enabling this in glibc shortly. So some of the benefits of TLE, apart from just a simpler programming model, in that you don't have to rewrite your code, your existing locking code just works, is that it provides this concurrent execution of critical regions, as we talked about, to give you better concurrency, more throughput. But other important features are it reduces lock thrashing. When you have multiple threads contending on the same lock, they're all sharing the same bit of data, the same lock data in memory, and you've got that lock data is ping-ponging around the different caches of the machine. Now the advantage of TLE and using transactions is you never actually modify the lock state. And therefore, you don't actually have to have a local copy of the data, the lock structure itself in your local caches. It reduces the amount of thrashing that goes on here. But also another important feature is for lock preemption. At the moment, if software takes a lock and that thread or process is suspended or paged out, swapped out or whatever, no other thread, no other process can make progress while that thread is not scheduled. In the case of a transaction, it's not a problem. Another thread comes along and it can actually reclaim effectively the lock by killing the transaction that's been suspended. That one will have to retry at some point, but at least forward progress can be made by other threads. This is just an example of what a TLE implementation looks like. I don't think we've got time to go through it in detail, but you can see essentially it just has to operate. It has to operate with both legacy locks and transactions. So it has to poll the lock initially to see if it's been locked by legacy software. If it hasn't, then it can start a transaction, check whether it's succeeded, check for a possible race condition where maybe some legacy locking code has managed to reacquire the lock before it got a chance to start the transaction, and then off we go. And we return without actually having to do any update of the lock variable, but we're now in transactional state. The lock is just trivial. If it's locked, that means it was a traditional legacy lock, do the normal legacy unlock code to unlock the lock. Otherwise, issue a T-commit instruction to terminate the current transaction. And it's as simple as that, more or less. The magic comes in something like the OK to retry function at the end, which is essentially using heuristics to decide for any given failure whether and how often to retry the lock. So everybody's probably pretty familiar with the SAP-HANA benchmark. If you've looked at transactional memory, this is the kind of poster child for transactional memory. This is a real-world example where people have published results using transactional memory. And I think the comment on the right is probably the most interesting one, which is it's saying that the most important thing for these sort of applications, which are using mechanisms to implement concurrency, to control concurrency, is to make it simpler. Because the difficulty of reasoning in a very complex piece of software about how to manage either locks or how to write lock-free code is a huge intellectual effort and very difficult to debug, and it can take many, many months or years to get this code working. With transactions, it may not give you the ultimate in performance you'd get if you spent those years working on it, but you can achieve very comparable results much more quickly. And so the graph here basically shows the speed up that we can get. Bottom line, just using conventional spin locks. That's in red. That's our baseline. The top grey line is, what we could achieve if we did the sort of ultimate in lock-free code. Essentially, we could get to have no concurrency control at all. And then the green lines below show what we can achieve essentially using HTM, which is a very simple replacement for the spin lock, using lock elision, as we've just talked about. This was implemented at a low level rather than using Pthreads, but the principle is the same. But that was one particular example where people actually were working at a low level. In this particular case, Twemcache, it's a Twitter Memcached application. This is an example of where the performance was achieved without any changes to the code at all. So this code base was just using standard Pthread mutex locks, and this was implemented using on a TLE implementation of the mutex locks in glibc, and so no software changes required at all. And that immediately gives you this increase in concurrency, such that we get something like a 40% reduction, increase in requests that can be processed per second by this server, and a 40% or so, 49% decrease in latency per request. There are some tail conditions in the end there, but generally speaking, this gave us huge performance uplifts without any need to rewrite our code at all. This was just another example of an application which benefits from transactional memory. So the DPDK cuckoo plus, so this is a data plane processing. This is the essentially for the flow classification routing tables in DPDK, which were implemented using a range of different attempts were made to optimize this particular lookup hash table. The best results, were gained by doing some very clever fine-grained locking. Required a lot of work to get that to work correctly, but just replacing the locking and the bottom line here with HTM was very straightforward to do, didn't require any complex rewriting of the code, and gave the researchers who were working on this the largest increase in throughput compared to the original fairly simple-minded implementation. So, conclusions. ARM is announcing to this audience today 2 new technologies in order to enable ARM and the open source community to begin to upstream and support these technologies. These are committed architecture technologies that we are going to be publishing within the next 2 weeks on developer.arm.com. You will be able to download the instruction set XML and have a look at it. They're designed to scale performance by exploiting our additional transistors that we have on our SoCs and try to address some of the slowdown due to Moore's law by extracting that additional parallelism from existing software, and this is the important point here. It can get it from existing software without us having to rewrite it for some new framework. SVE2 gives us the improved auto-vectorization, now with support for DSP media type code and hand-coded SIMD as well as auto-vectorization. And so it gives us this increase in fine-grained data-level parallelism. More work can be done per instruction. TME gives us easier lock-free programming for likely contended shared data structures, such as we looked at in those slides a moment ago. So it gives us additional scaling of concurrency for coarse-grain thread-level parallelism, giving us more work done per thread. And then together, SVE2 and TME may be able to combine together. If you have applications that can use both SVE2 and be multi-threaded, then you actually can get even greater performance scaling because you're now tackling Amdahl's law on 2 fronts rather than just 1. Enabling tools and documentation. I mentioned that the instruction set XML is going to be available within the next couple of weeks. There's a link there. You can go and check to see when it's available. There is literature on SVE, if you're not familiar with that already, available. That's the existing SVE rather than SVE2 on our website in the HPC area of developer.arm.com, and there's a link there to that. There are no changes to the ABI documents introduced by SVE2. The kernel stays the same, the procedure calling standard stays the same, no changes at all. The SVE2 literature, we will be providing more example code and programmer's guides for SVE2 very shortly. LLVM, there is work in progress. We are planning to upstream support for SVE2 and TME over the course of the next year, with the goal to have that all available upstream at the beginning of 2020. We have actually now good news. This is actually very, very fresh news. We have now actually got agreement from the LLVM maintainers that to actually start pushing the vector length agnostic changes upstream. So that's compared to the discussion we had this morning at 8:30. That's a major step forward. In the GNU tools, they already support SVE upstream. We've had support for SVE since GCC 8. And GCC 9 adds additional support and additional performance improvements. We're going to be upstreaming the SVE2 and TME support immediately once the XML is published, and that will include support for auto-vectorization and the new ACLE extensions for SVE2, and that will is targeting again for similar time frame, targeting the GCC 10 release at the beginning of 2020. But obviously you can also download the current version from upstream as well if you want to play with that. glibc will be adding support for transactional lock elision within the next few months. ARM tools, so proprietary tools, we have these will support SVE2 and TME. They're targeting the end of this year, the second half of this year, for the ARM compiler, debugger, and fast models. And the documentation we've already talked about. So that's it. Any quick questions?
How will this transactional memory
model interact with memory barriers? At what time is the memory actually modified? And, you know, what does it mean if you read and write, you know, this kind of thing. So that's the first question. I'll ask both questions since there's only one microphone. And then the second one is, when can we expect this to be implemented in silicon? Because, you know, you've talked about SVE for a while now, and the only processors we are seeing implementing SVE are pretty much the post-K ones. So,
so for the issue with memory barriers, I will punt. That's a much more complex discussion, I think, that we can talk about here. But I can certainly point you to some of my colleagues who actually have described the memory model for TME in a lot more detail. You're aware that the ARMv8 memory model is now described using the formal CAT language, and we have extensions to that to support TME as well, which will make that completely explicit. Regarding CPU availability, I am not in a position to announce anything about that. It is a committed architecture. There are implementation teams in ARM and in the ARM licensees who are looking at this, but there is no announced roadmap yet, and likewise for the actual architecture version as well. So until we are closer to the availability of those, we're not going to be making a big public announcement. This is a low-key announcement to enable you folks and other people in the open source community to start working on this and enabling the technology. But let me just say, it is SVE was very much an HPC targeted product. I mean, I'm not saying it won't appear in other devices as well, but that was very much its initial focus. SVE2 widens the scope of that to a much larger range of applications, including, you know, potentially clients and edge devices as well. So it'll be much, and the goal is that in the same way that NEON is currently a required feature for sort of open ecosystems in ARMv8, SVE2 will ultimately have a similar status to that. So it'll be effectively a required feature for open software ecosystems.
Nigel, one question on forward progress. Let's say the writer falls back to take a traditional lock, and then, you know, he's suspended. Are the readers allowed to make forward progress in that case?
Well, that would be a read-write lock. Okay, so I mean, there's no reason why you couldn't implement, for example, using a very similar mechanism, a read-write lock rather than just a simple spin lock. So you could do that. That would be a software architecture choice.
Okay.
Yes. At the moment, that example I showed you was just a spin lock. So essentially it waited at the beginning for any other locker rather than doing the kind of distinguishing between read and write locks.
Okay.
Yeah. Okay, everybody hungry? Okay, thank you very much.